Today we will solve some previous year questions on separation axioms. Our first question says, which is a 2 marks question, says give an example to show that a compact subset of a T1 topological space need not be closed. So we have to find such a T1 topological space which has some subset which is compact but not closed. Okay, we let x is equal to real line R and tau as cofinite topology and A as open 0 to 1, which is of course a subset of x. Now to prove that A is a compact set, let G be an open cover of A. Okay, so each element G alpha of G must be an open set. So since this is cofinite topology, so x minus G alpha contains only finite number of points, right? So let A1 be any point of A. Okay, so there must be some alpha 1 such that G alpha 1 from this set such that G alpha 1 contains this A1. Okay, now since G alpha 1 belongs to this set, which is G alpha 1 must be open, so x minus G alpha 1, so x minus G alpha 1 must contain some finite number of elements. So G alpha 1 contains all points of A except possibly some finite number of points of A. Okay, so for these all these points of A, we can find such a finite set G alpha 1, G alpha 2 up to G alpha n, which also covers the set A, right? So for every open cover, we can have a finite subcover for A. So A must be compact, but A is not closed in x tau. Why? Because if A is closed, then x minus A must be open, right? So x minus A should belong tau, or we can say x minus A, which is equal to minus infinity to closed 0 union closed 1 to infinity, can be expressed as union of some A alphas, where A alpha belong to tau. Okay, so is this possible? If A alpha belongs to tau, that means what? If any A alpha belongs to tau, then complement of A alpha can have finite number of points, right? But see, there are infinite number of points lying between 0 and 1, such that no A alphas contain these numbers. So each A alpha does not contain infinite number of points. So this equality is not possible, right? So x minus A is not an open set, so A is not a closed set. Our next problem, which is a 3 marks question, says prove that in a T2 topological space x tau, a sequence can converge to a unique limit point. Okay, so let xn be a sequence in X. So it must be a net, as I defined earlier that a net is a function on a directed set, right? So a sequence is also a net on the set X. If possible, let xn converges to two distinct points x and y. And since I have told that, since it is given in the question that x tau is a T2 topological space, so there must be two open sets such that x belongs to u and y belongs to v, and their intersection is null. Their intersection contains no points. Okay, so since xn converges to the limit point x, so there must be a k, a natural number k. Like, let me explain you a better way. Let a sequence converges to x, and this is y. Since they both are not same point, that means they are distinct points, so we can find open sets u and open set v. This is u and this is v, such that their intersection is phi. Right. Since I have told that xn is a sequence that converges to x, so there must be some element k belonging to natural number such that all other elements for all n greater or equal to k, xn will belong to u. That means if this is a sequence, all the elements after k will converge to x. And also, since xn converges to y as well, this sequence goes to this. This sequence converges to y, right? So we can write it this way. There is some r such that xn belongs to v for all n greater or equal to r. But we know that u intersection v is equal to phi. So there arises a contradiction. That means there must not be two limit points in a convergent sequence, right? So x must be equal to y. Hence, a sequence converges to a unique limit point. Our next question is 1 plus 3 equals to 4 marks question, which says define a normal topological space and prove that every compact T2 space is normal. I have already defined what a normal topological space is in my previous video. So let me explain you this here. Let us denote closed sets by squares or rectangles and open sets by circles. Okay, so for two disjoint closed sets A and B in a normal space, there must be two disjoint open sets U and V respectively, such that U contains A and V contains B, and also U intersection V is phi. Okay, so we have to prove that for every compact T2 space x tau, that space should be normal space as well. Okay, so let us take a compact space x tau and AB be two closed sets in X such that A and B are disjoint. Okay, now we take this as the whole space X and this one as A and this one as B, two disjoint closed sets. So X minus A and X minus B is for sure two open sets in X. Okay, now we are choosing open covers in such a way that this whole set including B intersection neighborhoods of all points in B. That means we are taking open cover in such a way that this whole set intersection one neighborhood of some point is an open set in G1. Another open set is this whole set intersection another open neighborhood in B. That means these all sets forms an open cover for B, right? Similarly, G2, where X minus A intersection neighborhood of y's, where y are elements of B, okay, forms an open cover for B as well. Okay, and since X is a compact space, and AB are closed set, so AB must be compact, and that is why we can say that there must be some finite subcovers G1 dashed and G2 dashed for A and B respectively, right? Since the A and B are compact sets. Now, by construction of G1 and G2, G1 intersection G2 is phi, right? And G1 dashed is a subset of G1 dashed is a subcollection of G1, and similarly G2 dashed is also a subcollection of G2. So their intersection must be phi as well. So this is how we can get two open sets G1 and G2 whose intersection is phi, as well as A is contained in G1 dashed and B is contained in G2 dashed. So this completes the proof, because this is the required definition of normal space. So X tau is definitely a normal space.